Bom dia a todos. Vamos lá. So, let me remind a few things in order to announce the main topic of this lecture. In this lecture, we will focus on the case of surfaces. So our n always will be 2. And I will talk about a density theorem. And in a minute, I will explain. So let's again remember the notation. T, the space of surfaces, x0, x1, x2, x3, and smooth of degree d. And then we will remove singular hypersurfaces. So let's assume that this is it is usually parameterized by a discriminant. Discriminant, this is a kind of this is a polynomial in the coefficients of all monomials which pop up here. Anyway, let's again. I will denote the point here by f. I will also denote sometimes by t. So when I mean a polynomial, then I will use f, and when I mean really the parameters, with these t's are just the coefficients of f, then I will use this t notation. So anyway, these are just two different notations for the same thing. So xt will be the surface induced by this one in P3. And so let me remember the Noether-Lefschetz locus. Oops, it's blurry. Noether-Lefschetz locus, maybe. Noether-Lefschetz locus is just T in T, such that the corresponding surface xt has a curve which is not a complete intersection of xt with another surface. So in some sense, this means that this curve here is not of this format. So we have this f. So maybe I will use also, let's say, this sometimes the notation ft, the polynomial f depending on the t also. So ft equals 0 and g equal to 0. So this means that the curve is not just two equations equal to 0. And what we discussed in one of the lectures, that this is the union of GS, G and S in N. I put a tilde also, and these are algebraic subvarieties of a T parametrizing let's say x, no, maybe surfaces containing a curve of genus G and degree S. usually I will write also d here, but with d will reserve it for the degree of the surface. But if you see, sometimes I write s instead of d. Then you just be careful about this. Anyway, and I put tilde because the complete intersection of xt and with another surface, they also give curves inside the surfaces. And so, and at the end, I have to remove all these complete intersection curves. And so what we did in Noether-Lefschetz theorem. And this was in lecture 17. So this was let's say for generic X, for generic surface, the only curve in X is a complete intersection X intersected with Y another surface, and so the proof of this, basically how it was working, we did Hilbert scheme, and then we wrote this Noether-Lefschetz in this format, and then this was equivalent to saying that all these components that we get from this Hilbert scheme argument, they are proper algebraic. So this algebraic is trivial, but so the proper algebraic subvariety of T. So once we prove that all these things are proper algebraic subvarieties, so we have a union, innumerable union of proper algebraic subvarieties of T, and it is well known that innumerable union of proper algebraic subvarieties, they do not fill the whole space. So this means that the complement of this guy here, it is they are surfaces which they do not have curve which is not a complete intersection.
Hossein, just a comment. I think in the theorem you want to say that the only curves in X are complete intersections, right? In plural, because it's not only one curve.
The only curves in X are complete intersection by. Okay, so the proof was that basically to analyze first to analyze these loci of surfaces containing genus G, degree S, and non-complete intersection curves inside surfaces, and then to see that this is a proper subset of T. Maybe I have to say something. For now on, whenever I am saying a complete intersection, it means that the complete intersection of X with another surface. Of course, the complete in in the next lecture we will see a lot of interesting complete intersection curves in P3, which lies inside surfaces, but they are not the complete intersection of X with something else. Anyway, we will see this in the next lecture. Anyway, this was Noether-Lefschetz theorem. Lefschetz, there was two proofs, basically, one topological and another one using integrals, or in a modern version using infinitesimal variation of height structure of Griffiths and his co-authors. But let's go to the main theorem of today. So today is the density theorem. So first of all, this theorem basically says that the complement of T, the complement of this guy in T is dense. Yeah. So let's say, yeah, exactly. T Noether-Lefschetz is dense, and this generic, actually generic refers outside the enumerable union of algebraic subsets. But now today we are going to discuss this density theorem, which says that NL itself is dense. Dense in T. And actually, if well, these are kind of historical terms, but if you want to have a look to Voisin's second book, page 151, well, there is a proof there, but I will try to study this density theorem from the point of view of perturbing the Fermat variety. So today our goal is a little bit to understand this this density theorem. So anyway, this is a kind of theoretical statement and not practical, because what this means that if you take X surfaces in P3 and then you can perturb a little bit one of its parameters, and then X tilde, after a little bit perturbation, there will be some perturbation such that X tilde will contain a curve which is not a complete intersection. But in practice, how to do this perturbation and so on, there is no algorithm. And so from the computational point of view, still we have a long way to go. Okay, so let's again remember this the framework that I was working. So the framework that I was working, it was for let's say the Fermat varieties. So I've worked with affine variety x0 equal to 1. So let's write the x0 to the 1 d to the which is 1 plus x2 to the d plus x3 to the d plus minus, and then perturbation. Now I am directly using the affine chart, and here basically for the perturbation I put just all these monomials. This was a G in I. Remember that 0, 1, t minus 2, and then this is to the 3, such that let's say 4 d ag or d, and remember that this was a g1 plus 1 d plus g2 plus 2d plus g3 plus g1 plus d, g3 plus d. And okay, so by some linear group action argument on P3, the automorphism of P3, we argued that this kind of perturbation would be enough. And let me remember the other two. I20, basically this were parametrizing holomorphic differential forms. So maybe I write and then beta in I such that beta 2 and 1. We just needed this one. And maybe let's say, so this is Hodge number H11 is just the cardinality of I11, and H20 is just the cardinality of of I20. In this case, I mean, we can write down a closed formula for both, but I will write just for H20. This filter not to be binomial of d minus 1 over 3. And also maybe let's remember this one also, that the cardinality of ID, it's also easy to compute. It is d plus 3 binomial d3, 3 minus 16. So this is the kind of the moduli of surfaces, the dimension of the moduli of surfaces, or the parameter space of surfaces quotiented by the automorphisms of P3. Okay, so let me remember. Then if you have a G here, let me, well, I am using G beta, whatever, B, whatever is here. Then we constructed this omega beta. Omega beta at the end, originally it was, let's say, x beta dx divided by, okay, maybe in this case, let me just for I11. It is for I11, it was F2. And integrated our delta zero as a, let's say, a Hodge cycle, primitive Hodge cycle on the Fermat. So this 0 here is just for primitive. X0 is the Fermat. So let me say xt is xt. And so we, in the case of Fermat, we were able to reduce this pole order at the end, up to some rational number, up to some explicit rational number, which will be important also, this rational number in our discussion, but for now I don't write it. So it became something like x beta eta. Let me write it. X beta, it was x1 dx2 wedge dx3 minus now x2 dx1 wedge dx3 plus x3 dx1 wedge dx2. And something that at the end we did again everything up to some explicit rational number. We computed this this integral, beta 1 plus d, beta 2 plus d, beta 3 plus 1d, and then explicit element in, I will not write again that, in q zeta d. So these are the computations that we did so far. Anyway, and but then so everything, the formulas are clear. It is I have written in my book. But then what we did, we introduced this matrix pi plus g, I in I d. So this is we call this one, let's say, delta 0, then p beta here, ID G in I in let's say G in ID and I in I20. So this was a matrix with a lot of 0 and a lot of these numbers in its entries, pi plus g. Anyway, and we saw that the kernel of this matrix. So let me. So in this case, what is let's say Hodge locus? In a moment, I will say that this is just the same another left Hodge locus. V delta 0 was just by given by z omega let's say beta delta 0. Now t, so actually equals and then beta I20. Maybe let's, okay, so let me remember. So this is my t parameter space. This was the Fermat. Our 0, I have my Fermat with the Hodge cycle delta 0. And if I go to this small near, I would just perturb Fermat to another surface, then I will have another surface xt, x0, and I can make the monodromy delta t of this delta 0. So the Hodge locus was basically in this case the zero set of all these integrals as a function on t, and for all beta in I20. And here I have to mention that these omega betas form a basis of H0 global holomorphic functions, holomorphic two forms. So this means that you take a basis of holomorphic two forms on xt, and you integrate over the cycle, and then you put the zero. So this was the notion of Hodge locus, but the point is that in the case of surfaces, we know Hodge conjecture. This is Hodge conjecture. In this case, it is what? It is Lefschetz 1-1 theorem. So after some details about the primitive and so on, this means that at the end of the t in of what I'm saying. If you take t if v delta 0, then xt contains let me say here t. Oh, sorry, it's for the delta 0. So xt contains maybe okay. First, so delta t. So delta t is a Hodge cycle. So by Lefschetz 1-1 theorem, it is given by curves c it, and so Ri rational numbers, CIT curves, and it turns out that these we can immediately verify that these CITs are not complete intersections of xt with another surface. At the end of the day, what we can conclude, v delta 0. V delta 0. So remember that this is a purely local analytic subvariety of t, and it turns out that it is a union of branches of many NLGS. So maybe I put in the picture. So you have the V0. Anyway, we define this V delta 0. So it was a locally analytic. It might be reducible. It might have many branches. And so the statement is that these locally analytic varieties, they are just branches of this global algebraic subvarieties of T. So it might be not one of them, but maybe many of them. But in the Hodge locus context, Hodge locus context, we just see locally around 0. And And so, but they are part of this algebraic set. Anyway, this means that at the end of the day, Noether-Lefschetz locus in the local context is we can reintroduce it as a V delta 0, and in order to understand the properties of the Noether-Lefschetz locus, we can try to understand the properties of this V delta 0. Okay, so far whatever I did before. Okay, so maybe so you see that whenever I choose different delta 0, there might be different components of the Noether-Lefschetz locus. And something also very strange. This one 2 years ago when I was at Harvard, I took it with Harris. These components of Noether-Lefschetz locus, they have scheme structures coming from the scheme structure, the Hilbert schemes. And from another side, this delta 0 has a scheme structure, analytic scheme structure, coming from the fact that this is just its ideal is just the ideal generated by these integrals. And it's very curious if there is, so far there is no result showing if there is any relation between these two completely different scheme structure. Anyway, these are, I don't want to focus on this. So maybe what else? So maybe I tell this rank Pi plus G. The rank of this Pi plus G, the upper bound is a trivial upper bound. So this matrix, that you see here, its dimensions are this one and this one, and this is much bigger than this number. So the rank of this matrix must be less, trivially less than d minus 1, 3, which was the H20, the Hodge number H20. And again, in the last lecture, I showed some elementary problem without really looking this what are the number PIG, that this rank will be always bigger than d minus 3, assuming that this matrix is not identically zero, and maybe let's say assuming that delta 0 is not a zero cycle. And okay, so rank of this matrix goes between this one and this one. Okay, so maybe again when I make some, and in the same way, so this in the same way codimension of component of, so this is not clear from my Fermat variety context point of view, but the same codimension of the components of identity, they are between d minus 1, 3, d minus 1, 3, and anyway, this is the rank of this matrix are just the codimension of the of the Zariski tangential space of this one. So partially we can see this statement using this statement and just near the Fermat. So I will make one definition. Maybe I make it here. So the components reaching this maximum reaching this upper bound, they are called general components. So if a component of Noether-Lefschetz loci is of codimension d-1 3, then it is called a general component, and otherwise, so this what means otherwise, this is the between d-3 and strictly less than d-1 3. These are called a special component. And in the case, okay, so what is general component of Noether-Lefschetz locus? Is just the component with codimension d-1 binomial d-1 3, and the special one strictly the codimension is strictly less than this one. Okay, so maybe before going to the topic of the course, about the density component, density statement that I told at the beginning. Actually, we will discuss this one, Chiliberto, Harris, Miranda, the union of a general component of Noether-Lefschetz is dense. This is dense in the usual sense, in the analytic sense, dense in T. Actually, we will, so this is a kind of stronger, even just this special component, they are, this general component, they become dense. Maybe I say a Harris conjecture. The number of special components is finite. This is a kind of Harris conjecture around 90 and then wasn't found the counterexample. So let's say the Harris was a conjecture. So this is a conjecture we already know counterexample, but then we have this Harris-Hossein conjecture that the special components are not Zariski dense. The union, let's say, the union of special components are not Zariski dense in T. Anyway, let's skip the history of these conjectures and so on. And okay, so let's return back to the topic that I want to. So what I want to do next is that we can produce infinite number of general components, so through Fermat. So let me explain the strategy to produce okay, so for this one, let me go to share a window. Or maybe maybe I will write it. Just a moment.
Sorry, is Harris-Hossein conjecture still open?
Yeah, this is open. This is Harris conjecture is false. Wasn't found a counterexample, But in Voisin's counterexample, they were not. They are not the union of an infinite number of a special component that Voisin found. They are not Zariski dense. So the new conjecture is that the union of special components is not Zariski dense. This is still open, but the Harris conjecture is false. Okay, so let me a little explain the strategy to handle a little bit these conjecture computationally, and this is the point that I want to. So, okay. So the point is that at some point I showed you that the Fermat variety has a lot of Hodge cycles. In particular, it has always more than 2 linearly independent Hodge cycles. So let's take 2 Hodge cycles. And the primitive one. And okay, so, and then of course, if you have a Hodge cycle, then you have this family of Hodge cycles, no? Or if they're linearly independent, then we using delta 1 and delta 2, I will have a two-dimensional vector space generated by them. So the idea is that to look for this V delta 1 plus R V delta 2 is, and these are, let's say, analytics varieties, V delta 1 R delta 2. And the point is that when R moves, the hope is that I will get a kind of pencil of these varieties, and at least in order to say that I have infinite number of general components, we can produce this infinite number of general components in this way. Okay, so, and actually the strategy works. Maybe I make this definition V delta. So they did now the 1 and 2. I have used delta 0 because I have the perturbed to. Actually, I have to make this notation because I 0t. Okay, maybe not to do this one. Okay, what I'm saying that before the delta 0, this 0 was referring to parameter t equals 0. So I have cut this 0 from my notation delta 1 and delta 2 because I will not need to consider the corresponding monodromy of these cycles. Anyway, V delta. What I want to say, let's call this delta. V delta is called very general, and that in a moment we will see if codimension of tangent space of V delta at the zero will be, this is the maximum one. And again, this is the very general implies general, because when the tangent space of some analytic scheme is of let me say in this way. Actually, for this one, you have to remember that the delta is given by holomorphic function 1 equal to 0. Holomorphic function, and then this d minus 1, 3 equal to 0. So the point is that V delta is the 0 set of binomial d minus 1, 3, 0 set of holomorphic functions. So what it means that the codimension of its tangent spaces, this means that the linear part of all these holomorphic function, they are linearly independent. This means that V delta becomes itself. This means that V delta is local complex intersection section, because among all these equations, we need all of them. We cannot remove some of them, and in particular, this implies that codimension of V delta is equal to d minus 1 to the 3. Anyway, in order to produce general component, I just need to find cycles such that this codimension of this guy is this one, and we know what is the codimension of this one. So codimension of T0 V delta is what? Is just rank of this Pi plus G matrix of delta. Sometimes I don't write delta inside, okay, but now I put it. And remember that at the end, this delta is just delta 1 or delta 2. And our integral is really linear. At the end, this is the rank of the matrix Pi plus G delta 1 plus R. This matrix plus R times the Pi plus G delta 2. So the Hodge cycle delta 1, we construct this matrix. They were the algebraic numbers, and then makes R times the another matrix, and this we have to compute this. And our wish is that this is to be the maximal one. So maybe this proposition I have not put in my book, but it is in it is an article of mine which will be appear in Rendicotti journal. This is very simple, actually, just linear algebra statement. If let's say, if at least we verify that this for delta 1 is the one that we need, d minus 1 to the 3. So this means that for r equal to 0, I know that I get a very general component, and T0 with delta 1, T0 the delta 1 is not a subset of T0 delta 2. Then let's say this one codimension of T0 V delta 1 plus R delta 2 is the maximal one for all R except a finite number. This is it is really easy linear algebra. So if you have two matrices and you make a linear combination of them, and you know that one of the matrices reaches the maximal rank, then for all except the finite number of values of R, it doesn't matter R Q or not, but because of the Hodge theory, we are just interested in R equal to Q. Then the rank of this matrix will be and if also you check that the kernel of one of the matrices is not inside the kernel of the other matrix. So you remember that this tangent space, we can recover it as a kernel of these matrices. So this is a kind of practical theorem. What this means, then codimension and we have pencil of tangent spaces. Pencil of tangent spaces T0 V delta 1 plus R delta 2. So let me so what we want to do, we started from this so that let me say in this way, we want to produce tangent spaces which are different from each other. When I am saying pencil at the end, in this case it means that let me say this. For the moment, all these tangent spaces are different. Different tangent space. So this means that when this R moves, I can produce different tangent spaces, and when the tangent spaces are distinct, this means that the corresponding Hodge locus also will be different. And anyway, the hypothesis of this proposition can be checked by computer for special examples of Hodge cycles and degrees. So maybe I say in this way. Let me see. Okay. For example, remember that we computed all these numbers. I showed that we can implement all these numbers here. When we pick up a random Hodge cycle, always it seems that this condition is fulfilled because if we interpret the randomness as being something generic, and this condition also can be checked once we are doing computations, and it turns out that the hypothesis of this proposition can be checked by computer. And maybe if you want, I will show you just the computer codes of just a moment. Okay, so well, anyway, for example, in the case of this is in the case of the Fermat surface of degree 6, and there are some issues that now I will explain. And then at the end we can write down and the code and compute the Hodge cycles and this matrix codimensions and so on. But maybe I explain something else before going to. Oh, I stopped. Okay. Okay. Let me say what I want to say. Just a moment. should just a minute. Okay, just one more. Okay. So the point is that we need to compute period, but it turns out that even these transcendental factors, which were appearing, in our period formula, are important for this study of the tangent space. At some point, I remember I recall that the periods of the middle parts they have there are some zero integrals there, and there are some non-zero integrals there. But at the end, it turns out that we have to define something like this. All the things becoming d minus 2. And at the end, this we have to compute the gamma factors. And in this case, this gamma factors this beta factors becomes also something algebraic, and we have to implement all these things inside our period formula. And after this one, we try to implement in the computer. So the point is that we cannot in the computer. There is no gamma of rational function because they are transcendental numbers, and whatever is implemented, they are just some algebraic numbers. Anyway, there are a lot of things to say, but I will stop here.